K8BYP with the fourth video in the series on antenna and transmission line theory. I'm going to look at feed point tuning considerations and where feed points are treated as circuits. And this is a jumping off point for understanding why they aren't and why it's a myth that we can tune antennas externally. Let's say there are 5 cases for antenna feed point conditions. The first one is that the antenna's feed point resistance R is equal to R sub naught of the transmission line. The R sub naught is usually 50 ohms. If the antenna is also 50 ohms R, there's a perfect match, 100% power transfer, no reflection, 1-to-1 SWR. The second case, which is interesting to see on a TDR, a time domain reflectometer, is when R of the antenna is not equal to R sub naught, but reactance is 0. That's called a resistive mismatch, and it needs a resistive transform. Yes, we could put resistors at the feed point to correct that, but it would simply waste power. So that requires a reactive matching network with conjugate matching, such as a L or a pi or T network. A bandpass network could be used, but it's a major waste of time. What that complex conjugate network does is allow transforming resistive values only, not reactive. It is an absolute myth that we can take a feed point with R plus X and use a tuner to tune that out. Can't be done. It says Radio Engineer's Handbook written by a PhD. ARRL doesn't like that. Tell them to go read the book. Case 3, R is equal to the transmission line characteristic 50, but there is a residual reactance at some frequency. Remember the concept from the third video of residual reactance is where there's 2 kinds of reactances and they effectively cancel part of each other out. Might be an inductive 100 and a capacitive 10 that leaves a residual inductive 90. That can be corrected with simply a component with the opposite sign of X. That's the simplest case. The fourth case is where R, and that's for series circuit, simple case. It gets much more complicated when R is equal to R sub naught plus or minus X in parallel. That requires a complex transform. But again, the network cannot transform R plus X and R plus X. It's got to transform resistances. Fifth case, both factors are screwed up in the antenna. The resistive factor is off, and there's also a reactance. That's another case of complex transform. It's interesting to notice that we can see the case 2 on a TDR, a 50 ohm line and a 60 ohm resistive antenna. We'll get a reflected pulse. In a TDR, we can send a square wave up the line, a pulse up the line, and if there's a resistive mismatch, we'll get a square pulse back, except that it'll be rolled off a bit by line losses. That shows us something very interesting. That's what happens when the load is purely resistive. Guess what happens when there's an S component? That pulse does not come back square. Very, very important. These diagrams show why it is a complete myth and fallacy that we can tune an antenna at the feed point. The top diagram on the left, generator, RF generator, maybe looking down the feed line to a feed point, and we've put the antenna analyzer on the feed point, and it reads R50 minus J12. Well, it's 50 ohms. That's correct, because it's a 50 ohm line, but there's an annoying 12 ohms capacitive reactance hanging around. As far as magnitude impedance, that works out to square root of the squares, Pythagoras, that works out to 51.4 ohms. You might not even notice it across 100 feet of feed line. In fact, you probably won't. But it is a mismatch. And the problem is that X12 is not a real capacitor. That's something with antenna fields, and that portion of the energy is not being emitted because in an antenna, that R value is through the antenna transfer function out into space. The R value is what antennas the energy, and the X is swapped around in fields and either sent back to the feed line or dissipated. It's a loss. And I'll show you later from antenna physics, advanced physics, that loss is not just a little bit of loss. There's a factor in advanced antenna theory that suggests that the increase by adding more power is to the fourth power. It is a major improvement. So don't fall for the thinking that 10 watts forward and 1 watts back, that's only a tenth difference. Oh no. We can equate that to a circuit generator, no transmission line, R50 minus 12 capacitor. We don't need conjugate tuning for that. If you remember case 3, where R equals R sub naught, give or take a little bit of reactance, in a circuit we could effectively tune out that minus 12 capacitance by putting a plus 12 inductor right there, or any place in the circuit, just so it's in series. On paper, the minus 12 and plus 12 cancel and leaves R50. Remember in the first video, I made very specific mention of fields and components are conserved if they don't dissipate. In reality, there are small losses. In reality, an inductor that's not shielded will spew fields all over the house. But by general theory, they conserve. In the antenna, it's just the opposite. That X12 in the antenna is trying to couple that field to the house or trees or the ground, and much of it will be wasted. It's more than just obvious to say that that is what causes reflected power. Yes, it's stating the obvious. If there's an X12, there's a reflected energy, but it's not obvious that it's energy stored in the antenna and returned back down the transmission line, not radiated because it's not part of the R component. This fantasy of being able to do conjugate tuning and tune the antenna is illustrated by this literal circuit. If we put an inductor of plus 12 in the circuit, does that make the capacitor disappear? No. Under a crude but false theory, we say that the two cancel each other. No, they don't. The current may be the same, as I showed you in video 3, but there are high voltages swapping back and forth, which indicate that the components didn't go away, but the phase angle of the circuit has been corrected to 0. So there's real power in the resistor. But that's after fields were stored and are sloshing back and forth between those two components. And that represents energy loss, either because the components are lossy, they're spewing some fringed fields out, or the initial energy to charge this system had to first charge that and the inductor to reach an equilibrium condition, and that energy did not get dissipated in the resistor. And that's precisely what's happening in the antenna. Therefore, it is impossible to make that X12 go away in the antenna just by putting a 12 ohm inductor here. It will appear to the generator that this is R50, but it is not. The condition of the antenna has actually been made worse by tuning it, in a sense, because now more energy is being delivered to the antenna for more to be lost there. Yes, there'll be some more emitted through the antenna transfer function into this resistance, into emission into free space. It also increases the losses we shoot ourselves in the foot. Yes, the transmission line's happier. Yes, the SWR meter thinks it's happy. The transmitter looks happy. All is not well. As I said before, antennas are tuned. Antennas are electrical mechanical devices. They are tuned by their length, wire diameter, height above ground, location with other objects, on and on and on. Absolutely nothing is done here. Absolutely nothing is going to change the nature of that antenna. Does putting an inductor here change the length of the dipole arm? No. Will not change the antenna tuning. Unless maybe, except maybe in the case that putting something at the feed point of a VHF or UHF antenna affects the field associated with this. And at VHF, a little capacitance, a little admittance at the feed point will thoroughly screw an antenna up, and it can't be fixed. For example, that put up a VHF or UHF antenna and bring a piece of wood near the feed point. Watch what happens. It'll send a match right down you know where, because wood has an extremely high dielectric constant and is absorptive.